All right, folks, our next presenter is Sarah Kintner. Sarah Kintner is a hydrogeologist with Hydrometrics in Helen, Montana. She has a bachelor's degree in geology from the University of Wisconsin and a master's in environmental science from Washington State University. Sarah assists mine clients in water management, baseline characterization, modeling, and permitting. She is going to speak to us today on in situ study of groundwater nitrogen attenuation in wetland sediments. So please welcome Sarah.
Okay, good morning. So I'm Sarah with Hydrometrics. This talk is going to be a little out of place this morning. It's not so much reclamation, but I filled a spot that opened up at the last minute. Like Mike said, I will be talking about nitrogen attenuation study that we performed at Black Butte Copper. So first I'll give a little bit of an overview of the site and their discharge plan so that you can understand the study that we did, and we'll go through results and discussion. So a bit of background about Black Butte Copper. It's located in central Montana, 17 miles north of White Sulphur Springs. It's within the Sheep Creek watershed, and as I'm sure we're all aware, it's 19 stream miles from the Smith River. It is an underground copper mine with a high-grade ore body. So Tintina's MPDES permit has them discharging water from the water treatment plant to UIGs, which are shown here in orange. The UIGs are located in the Sheep Creek Valley and discharged to a shallow alluvial aquifer. There is no direct discharge to surface water. However, this discharge is covered under a surface water permit, and that is because of the hydrologic connectivity between that shallow aquifer and surface water bodies, Sheep Creek and Coon Creek. So here I've added the potentiometric surface, and as you can see, the water in that shallow aquifer travels approximately parallel to Sheep Creek, and then that aquifer pinches out at the mouth of a bedrock canyon. And so that pinching out causes the groundwater to well up. It creates a wetland system, which is shown in blue, and then that water eventually discharges into Sheep Creek and Coon Creek. So here in pink is that seepage area in Coon Creek, and then yellow is the seepage area in Sheep Creek. And some piezometer data from the wetlands shows that the water table in the wetlands can be about 1 to 2 feet above the ground surface, which just further indicates that hydrologic connectivity in the upwelling that we see. So I'm going to talk a little bit about their permit. Note that this permit is based off of DEQ Circular 12A, and it does not include any of the narrative translator values that are being proposed at this time. So with that caveat out of the way, with the exception of total nitrogen, all constituents in the discharge water will be below non-DAG criteria. They are proposing to discharge about 375 gallons per minute into the UIGs. And total nitrogen is the exception to the meeting the non-DAG standards. So total nitrogen is a seasonal limit. It applies during the growing season, so July through September. And total nitrogen is limited to 0.09 milligrams per liter in the surface water. And so the surface water background concentration in Sheep Creek is 0.12 milligrams per liter, I believe. And Tintina's anticipated discharge is, or I guess what the value of the permit is based on is 0.59 milligrams per liter. So these are all very low concentrations. And that 0.59 is actually the anticipated concentration times a safety factor of 1.75. So with all those numbers out of the way, the simplification of this is that they have discharge from the water treatment plant during the growing season, so July, August, September. If that concentration of total nitrogen is above the non-DAG standard, then that water needs to go to a storage pond and be held throughout the growing season. If at some point the concentration is below non-DAG, it could go to the UIGs, but that's not necessarily anticipated. So then October through June, the non-growing season, the non-DAG standard does not apply. And so the water treatment plant discharge can go straight to the UIGs, and then that storage pond will be emptied. So as I mentioned, the permit is based on that discharge concentration of 0.59, which exceeds the surface water total nitrogen standard. And Tintina wanted to evaluate what would the actual nitrogen concentration in the groundwater in the wetland system be prior to discharge to surface water if we were to account for attenuation of the wetland sediments. So the permit is just based on water goes into the aquifer and comes out in the stream, but there's a massive system of wetlands in this area. So that's where hydrometrics comes in. It's well documented that wetland systems can facilitate nitrogen attenuation, and as I mentioned, there's a large wetland system. Again, the UIGs are here in orange. The average distance that discharge would travel through wetlands is about 100 feet. In some areas, it's up to 500 feet. And so this begs the question, can the wetlands remove the nitrogen and get it to below the non-dig standard prior to discharging to surface water? So before we get into that, we're going to review the nitrogen cycle really quickly. The nitrogen cycle is notoriously complex. I've studied it since grad school, so I've shown you just a simplified version here of the nitrogen cycle in the wetlands. So you have total nitrogen coming in. Nitrogen is cycled around in a myriad of ways, and then it can ultimately be removed or attenuated through 4 main processes. So denitrification is your microbial process where nitrate is converted to gaseous N2 and is lost to the atmosphere, and literature suggests that that's the major process that occurs in wetlands as far as nitrogen removal is concerned. You can also have plant storage, so plant uptake, and then when those plants die, long-term storage in the soil through soil organic matter. And you can also have short-term soil storage, like ammonium adsorption. So let's consider how to answer my question. Can the wetlands remove nitrogen to below the non-dig standard? To answer this question, we need to know some wetland attenuation rates, and then we need to apply those to our system based on the wetland size and our inputs and anticipated, our criteria that we want to meet. So to begin, Hydrometrics conducted a push-pull test in the wetland area. So a push-pull test is an in-situ testing method that's particularly well suited for determining reaction rates. And so what this involves is first injecting a tracer solution into the groundwater system, so like through a piezometer, and then you extract or pull that tracer out over your study period. And so for our study, we injected total nitrogen, and then we also injected a non-reactive tracer, bromide. So bromide is not expected to have any sort of chemical reactions, and so that allows us to account for dilution. So at the end of the study, you can plot concentration over time. You can calculate the concentration of nitrogen that you anticipate based on dilution alone using that bromide data, and then you can compare that to your observed concentration. And if your observed concentration is less than the expected concentration, you know that you have removal because more nitrogen is missing than can be accounted for with dilution alone. So during the last week of September, Hydrometrics conducted the nitrogen attenuation study. Our field plot are shown here on the center figure. And so here's the UIGs again in orange in the wetland system. We had 4 study plots, each with 3 piezometers that were installed about 2 to 4 feet below ground surface in saturated sediments. On the left, you can see a picture of one of our study plots, and the piezometers are shown in blue, just so you get an idea of kind of what this area looks like. And then we used a peristaltic pump to inject the sample solution and then to pull out our samples as well. So we worked with Energy Labs in Helena to come up with our injection solution. And in the end, it contained 2 milligrams per liter of total nitrogen, 20 milligrams per liter of bromide, the non-reactive tracer, and then calcium and bicarbonate so that the general water chemistry matched the anticipated discharge. And so we collected background samples from each of the piezometers, injected 2 liters of the solution, and then collected samples over a 48-hour study period. This did involve night work. I was at a wedding, so I didn't have to do it, so that was lucky for me. So moving on to our results, the background concentration of total nitrogen in the piezometers ranged from 0.1 to 1.14 milligrams per liter, and that's compared to our injected concentration of 2 milligrams per liter. This range in background is likely due to the agricultural use of the pasture. There were cows grazing during this test, and our piezometers Some of them actually had to be sectioned off from the cows and all of their nitrogen-containing cow pies. So that's the range. And then bromide in the background concentrations was less than the detection limit compared to our injected concentration of 20 milligrams per liter. So here are some initial results. The expected concentrations are shown in red, so that's based off of dilution alone, and then the observed concentrations are shown in blue. These plots represent our minimum, our average, and our maximum removal rates. And so as you can see, blue is less than red, and so this indicates that removal was actually occurring, and this wasn't just the effect of dilution. So then there's some math I'm going to gloss over, but give you the highlights. We then need to calculate the removal rate. So nitrogen removal in the wetland systems follows a first-order kinetic removal equation. And so on these plots, it's a log normal plot. On the y-axis is your nitrogen concentration with the effects of dilution removed, and then time is on the x-axis. And so you plot a linear trend line through your data, and the slope of that is your kinetic removal rate. So now that we have a rate constant, how do we apply that information? We have to do some more calculations based on the wetland system size and the expected nitrogen inputs. So first we can calculate a residence time. We know our anticipated starting concentration, the 0.59. We know we want it to get to the non-DEG standard of 0.09. So how much time does it take to do that? And the answer is 23 to 42 hours based on our average and our minimum rate constant that we observed. So 23 to 42 hours is a start, but it really doesn't mean anything in a wetland system. And so we need to convert that time to a migration distance. So this is your rate times time. And we can use the aquifer properties to come up with a linear velocity, how fast the water moves through that sediment. And so 23 to 42 hours is equivalent to a migration distance of 5.1 to 9.3 feet in our wetland system. So my initial question is, can the wetlands reduce total nitrogen to below the non-DEG standard? And we're almost there. We know that we need 5 to 10 feet of wetland sediments. So the question is there enough wetlands? And the answer to that question is yes. We need 5 to 10 feet of migration distance based on this study, and the wetland systems on average would have a travel distance of 100 feet, in some places up to 500. The smallest is 10 to 15 feet. And so this indicates that, yes, we would expect that the wetland systems would be able to remove the nitrogen to below the non-DEG standard. So discussion and conclusions. We would expect that there would be similar nitrogen attenuation rates during operations as we observed during the study. And that's because we use an in situ testing method in the UIG area, so our environmental conditions were, what they will be during operations, and our injected water quality, or our injected solution had a water quality that's similar to the discharge. And then the study was performed in the last week of September, and so that brings in a level of conservatism. So the last week of September, it's cold, and we would expect attenuation rates to be lower than during most of the growing season. And that's because the cold temperatures inhibit denitrification and plant uptake. So our attenuation rates are probably lower than you would see earlier in the year or in the growing season. And then this analysis doesn't assume any credit for dilution in the groundwater. So the UIGs will discharge water into that shallow aquifer. The water will mix, then go through the wetlands and into the surface water. And we did our calculations based on that undiluted concentration in the discharge water. So in conclusion, this study shows that when you account for, nitrogen attenuation in the wetlands, the nitrogen in the discharge water would be sufficiently attenuated to meet the non-DEG criteria prior to entering surface water. So with that, I will take any questions.
Great, thanks, Sarah. Any questions for Sarah?
So it's been a while for the nitrogen cycle for me. Is there any question or concern about saturation of nitrogen in those wetlands? And a residence time or a time at which that might not function in the same way?
I do not believe so. In these wetlands, we're putting in a pretty small amount of nitrogen, so the background concentration in the wetland water was 0.1 to 1.14, I think, and we're expecting discharge concentrations below 0.6, and then it'll dilute with groundwater. So we're really not like increasing the nitrogen load in the wetland systems.
If your piezometer data shows that the groundwater should be 2 feet above the surface, how do you have willows, which can't be in a real wetland? You should have cattails or something like
You know,
that.
you and I chatted at breakfast, and I told you I wasn't a wetland person. That is a great question. I can get back to you on that.
Any other questions? I don't see any. Thank you, Sarah. That was a great presentation.